So to evaluate this triple integral for this infinite domain, so to speak, well, because in at one point we will need to, where's my, so we will need to express this as an improper integral, that is with limits at infinity. So number one, if we think of a sphere with with infinite radius, well, that means that radius is going to increase from negative infinity to positive infinity in all directions, in the x direction, in the y directions, in the z direction. That means our integral would look like the triple integral from negative infinity to positive infinity, negative infinity to positive infinity, negative infinity to positive infinity of e to the negative x squared plus y squared plus z squared to the 3/2. Let me call this dz, dy, dx. But number one, we don't have the tools to evaluate this integral. We can't evaluate this integral with the methods that we know, unless we could express this function as a Taylor series with three variables, which actually that is a thing, but we don't do that. We don't cover it in this class. And on top of that, even if we had the chance to evaluate this integral, well, look at the limits. Those are 6 limits involving infinity. Do you feel like evaluating 6 improper integrals, setting up 6 limit problems? Well, the power of spherical coordinates is going to reduce this to only one single improper integral. The remaining integrals are going to be the regular integrals. Well, let's think about this. Okay, so if we think of the sphere, okay, let's think of the sphere in the first octant. I'm going to do the first octant only. But of course, let's use our imagination and think of the entire sphere. So I'm going to go straight to spherical coordinates. So number one, how is the radius changing in this case? so the radius is increasing indefinitely, right? That means the radius can be, well, it's actually greater than 0. So maybe it contains the origin and increases indefinitely all the way to positive infinity, right? So that's going to be those are going to be our limits for what's it called, for the radius. Well, what about the angle? Okay, phi, the drop down angle. So what do you think about the limits for the azimuthal angle, the drop down angle? Any ideas? How would they change? Now, I think that we're considering the entire sphere here, right? What would be those limits? Again, the azimuthal angle is the angular descent that takes us from the North Pole all the way to the South Pole. What would be those limits then? Pi? Just pi? So what? 0 to pi, right? I mean, would that make a difference for a sphere that makes that gets like an infinite radius? That doesn't make a difference, because you can have a unit sphere, a sphere of radius 3, a sphere of radius 1,000,000. The angle, it's still the same. Of course, it's going to take you longer to go from the North Pole to the South Pole on a big sphere, but it's still going to be the same angles anyway. What about the polar angle? What do you think about that one? Would that make a difference for an infinite sphere? The round angle? No. So theta varies between 0 and 2 pi. All right. So let's set up a triple integral in spherical coordinates that represents this this infinite region. Well, so that'll be okay. The outermost integrals are for theta, that is 0 to 2 pi. The innermost, the second, or rather the middle integral will have limit 0 to pi, and 0 to infinity for the radius, the limit of integration. And I'm going to convert this, oh, this is supposed to be negative outside. So I'm going to write this x squared plus y squared as rho squared, okay? So that'll be e to the rho squared to the 3 halves. And dc dy dx, what does that become? Rho squared sine phi d rho d phi d theta. And well, we can simplify the exponent on rho in the integrand. That's going to leave us with the integral from 0 to what's that? 0 to 2 pi, 0 to pi. And I'm going to write this integral already as a limit problem. Limit as b approaches infinity of the integral from 0 to b of e to the rho cubed, rho squared, sine phi, d rho, or negative, yes, to the negative, d rho d phi, d theta. And we can easily do a u substitution for this exponential function, because what do we have? Rho cubed, we have its derivative, which is 1 degree less. So let's set it up. Let's do u equals to negative rho cubed du equals to negative 3 rho squared d rho. That is rho squared d rho equals to negative 1/3 du. Okay? So, let's change the limits also. So that is u of 0, that is negative 0 cubed, which is still 0, and u of b, that is negative b cubed. So what are we going to have then? Well, let's write down our new integral. So this d rho will be replaced with negative 1/3 du, but I'm going to write the negative 1/3 outside of the triple integrals from 0 to 2 pi, from 0 to pi, and that's limit as b approaches infinity of the integral from 0 to negative b cubed of e to the u du sine phi d rho d theta. All right, that looks ugly. Okay, so that's e to the u du sine phi d rho, d phi d theta. All right, so let's integrate e to the u, which is simply e to the u. So negative 1/3 integral from 0 to 2 pi, integral from 0 to pi, limit as b approaches infinity, that's e to the u evaluated between 0 and negative b cubed. Don't forget the sine phi, d phi, d theta. So the remaining part of the problem, that's upper limit minus lower limit. Again, we will integrate the sine function, and then we will integrate with respect theta. So the pattern is the same, all right? So that's negative 1/3 integral from 0 to 2 pi, integral from 0 to the pi. What's that? Limit as b approaches infinity of the quantity e to the negative b cubed minus e to the 0 times sine phi d phi d theta. Right? Now let's compute this limit. So what is this quantity? Where is this quantity going to go as b approaches infinity? 0. And what is e to the 0 again? Did I just 1? All right, so here we're going to be left, check this out, we're going to be left with a negative 1 right here. So this negative 1 that we get inside of this bracket, multiplied outside with the negative 1/3 to turn it into a positive 1/3. All right, so let's see. So that is 1/3 integral from 0 to 2 pi, integral from 0 to pi, and that's the integral of sine phi d theta. And we're almost there for this one. So the integral of sine, again, that's negative cosine Evaluate it from 0 to pi. Don't forget the d theta. And well, evaluating cosine of pi minus cosine 0, that's a negative 1/3. Integral from 0 to 2 pi. Cosine pi minus cosine 0. Okay, so again, let's simplify the inside of the parentheses. That is, cosine pi, isn't that negative 1? Cosine 0 is 1. The end result right here, what is that? Negative 2, right? The result inside of the parentheses, that's a negative 2. How about we multiply that negative 2 with the negative 1/3 outside of the integral? That's going to give us, what's that? 2/3, positive 2/3. Integral from 0 to 2 pi d theta, which means 2/3 theta from 0 to 2 pi. And then what is that going to be? 2/3 times 2 pi minus 0, which equals 4 pi over 3. All right? Which means the integral, what does that mean? It's an improper integral, right? So what do we need to conclude about it? It's only one word. Converges, right? Converges. Right? So the integral converges. Right?